All right. Um, so this is a example, second example. In this example, rectangular voltage wave with a magnitude of 1 per unit is initiated at bus bar 1 and propagate toward bus bar 2. So the problem consider a time interval of 180 microseconds during which multiple reflections and transmissions occur along the lines. So the system consists of two transmission lines with different lengths, surge impedances, and propagation velocities, as well as a short resistor connected to one of the buses. So these parameters significantly influence how the traveling wave behaves and indicating how it reflects at impedance discontinues and interact with the network elements. By using the given data, including line lengths, surge impedances, and wave speeds, the accommodated overvoltages at each bus bar can be determined by using of previous equations, showing the importance of transient analysis in insulation coordination and system protection device. So this slide, sorry, the quality is very low. This slide focuses on the calculation of wave travel times and the normalization of the time axis for transient analysis in the given transmission system. First, the, the propagation times for each line are determined using the ratio of line length to wave velocity. For line 1, the travel time is approximately 90 microseconds, while for line 2, it is about 30 microseconds. So these values represent the time required for a traveling wave to traverse each line once, you know. Next, the base time step theta is selected, which is taken as the travel time of the shorter line is around 30 microseconds. This choice simplifies the analysis by allowing all events to be expressed as multiples of a common time unit. So using this base, the total observation time of 180 microsecond can be converted into a dimensionless form. We can find 66 theta. So similarly, the travel times of the individual lines are normalized, giving them theta 1 is equal to 3 theta for line 1 and theta 2 is equal to 1 theta for line 2. So this normalization process is very useful in lattice diagram analysis, so as it allows the tracking of incident, reflected, and transmission waves at discrete time intervals. It simplifies the visualization of wave interactions at different junctions and helps in systematically determining the accumulation of over voltages at the bus bars. Okay, this slide presents the calculation of reflection coefficient and the equivalent resistances, which are essential for analyzing wave behavior at discontinuities in the transmission system. So first, the reflection coefficient at the sending end can be calculated. We can obtain the k r k k or s is equal to -1, indicating a complete reflection with priority reversal due to the short circuit condition. On the receiving end, the reflection coefficient is can be found to be KRR is equal to 1, which correspond to an open circuit condition where the wave is fully reflected without any inversion. Okay, the slide then evaluate the equivalent resistance forward formed by parallel combination of the surge impedances and the shunt resistor. So especially the parallel combination of um, 75 ohm and 230 ohm result in approximately 56.56 point ohm, while the combination of 300 ohm with and 230 ohm gives about 130.19 ohm. So these equivalent values are crucial for determining how the travel waves split and reflect at junctions. Overall, this step established the key parameters needed to construct the lattice diagram and accurately compute the over voltage buildup at different points in the network. So this slide explains the concepts of reflection and transmission coefficients for traveling voltage waves at the junction between bus 1 and bus 2 and bus 3 in a in this case study. So the reflection coefficient KR 1, 2, and 1 can be calculated using the surge impedance values of the connected lines. By substituting the values, the result will be 0.683. The negative sign indicates that the reflected voltage wave changes its polarity when it returns from bus 2 back toward bus 1. So this means that part of the incoming wave is reflected back with an opposite sign due to the large impedance difference between the two buses. The transmission coefficient K, T1, 2, and 3 represent the portion of the voltage wave that continues forward from bus 1 through bus 2 and toward bus 3. So its value can be calculated as 0.317, which can also be obtained using the relationship between in this relationship. So this shows that only a smaller portion of original wave is transmitted forward, while the larger portion is reflected back. So these coefficients are very important in transient analysis because they help us understand how switching surges or lighting surges propagate through transmission networks and how impedance mismatches affect wave behavior. All right. This slide explains the reflection and transmission coefficient for traveling voltage wave moving from bus 3 toward bus 2 in the power network. So the reflection coefficient R3, 2, and 3 is can be determined using the surge impedance values of 130.19 and 75. So by applying the formula, the result will be 0.269. So since the value is positive, the reflected voltage wave returns toward bus 3 without a change in polarity. So this indicates that part of the incident wave is reflected back to the due to the impedance difference between bus 3 and bus 2, but the reflected wave maintain the same direction of voltage sign. So the transmission coefficient K, T, 32, and 1 represent the portion of the traveling voltage wave that continues through bus 2 and moves toward bus 1. So its calculated value is equal to 1.269. So which can also be verified using the relationship of this relationship. And in general, a transmission coefficient greater than 1 means that the transmitted voltage wave becomes larger in magnitude due to the impedance conditions at the junction. So this is a common phenomena in traveling wave analysis and is especially important when studying switching surges and lighting transients in transmission systems where voltage amplification may occur at certain points in the network. Okay, this slide illustrates the lattice diagram of traveling waves propagating between bus 1 and bus 2 and bus 3 over time. So the vertical axis represent time in multiples of theta, while the horizontal axis shows the physical locations of the three buses. The initial voltage surge starts from bus 1 with a magnitude of 1 per unit at time 0 and travels toward bus 2. After travel times of 3 theta, um, 3 theta, you can see here, travel of 3 theta, the wave reaches bus 2, and here, so this is 3 theta, and where part of the wave is transmitted toward bus 3 and with a transmission coefficient of 0.317, and another part is reflected back toward bus 1 with reflection coefficient of minus 0.683. So the negative reflected coefficient indicates priority reversal. So the reflected wave returns to bus 1 with an opposite sign and reaches bus 1 at 6 theta with a magnitude of approximately minus 0.683 per unit. When combining with the original voltage, the resulting bus 3 voltage becomes approximately 0.682 per unit and reaches it at 4 theta here. Here. And uh, where further reflection and transmission will be occur, and additional smaller waves such as 0.0852 per unit are generated due to repeated reflection between bus 2 and bus 3, and these successive reflections gradually modify the voltages at each bus and indicated that the voltage at bus 2 becomes 0.72 per unit, and while the final voltage at bus 3 is equal to this value 0.8044 per unit. So this lattice diagram is very useful in transient analysis because it visually tracks wave propagation, reflection, transmission, and resulting voltage buildup in a transmission network. So you can see a part of the wave will be reflect to the bus 1, and the rest of the wave will be forward to the bus 3. Okay, this diagram summarizes the final voltage values at bus 1, bus 2, and bus 3 by adding the incidence, reflected, and transmitted traveling wave components obtained from the lattice diagram. For bus 1, the total voltage can be calculated as V bus 1, 1 per unit. This shows that after the reflections return to bus 1, the negative and positive reflected components cancel each other and resulting in the bus voltage returning to its original value of 1 per unit. And so these two values can be actually cancel each other, and we will have the 1 per unit at the end. For bus 2, the voltage can be calculated in two equivalent waves, these waves or these waves. So first, by summing the transmitted waves to the right of bus 2, we obtain V bus 2 is equal to the summation of these voltages is equal to 0.719 per unit. Alternatively, by summing the wave components to the left of bus 2, we can get the same value. So both methods produce the same result, confirming the accuracy of the traveling wave analysis and demonstrating energy consistency across the system. So for bus 3, the final voltage can be found by adding all transmitted reflected wave contributions reaching that point. So V bus 3 is equal to 0.8044 per unit. This indicates that bus 3 experiences a higher accumulated voltage due to multiple successive reflections and transmissions. These final voltage values are important in transient studies because they show how surge propagation affects different points in the network and help you evaluate insulation, coordination, and system protection requirements. This is another example. This example focus on the calculation of transient over voltage in transmission system following the injection of a traveling wave, especially a rectangular voltage wave with a magnitude of 400 kilovolt is launched from busbar 1 toward busbar 2 at time 0, and the objective is to determine the accumulated over voltages at each busbar after 650 microseconds. So the system consists of two transmission lines with different electrical parameters, including lengths, inductances, and capacitance, as provided in this table. Line 1 is significantly longer and um, has a higher inductance, while line 2 is shorter with relatively higher capacitance. Additionally, a shunt resistor is connected at the far end busbar 3, which plays a key role in damping reflections and influencing voltage magnitudes. So the problem essentially required analyzing wave propagation, reflection, and transmission phenomena across discontinuities in the network. By tracking the incident and reflected waves over time and considering the impedance mismatches at each junction, the total overvoltage at each busbar can be determined. So this type of analysis is crucial for installation coordination and for ensuring the reliability and protection of high voltage transmission system. Okay, in this slide, the key transmission line parameters are first defined and then used to derive the fundamental quantities required for traveling wave analysis. The inductance and capacitance per unit length for both lines are given, as you can see here, allowing all of this given value, allowing us to calculate the surge impedance by using of Z equal to square root of L over C. So accordingly, line 1 has a significantly higher surge impedance, approximately 600 ohm, compared to line 2. So line 2 is around 225 ohm. So indicating a strong impedance mismatch that will lead to reflections at the junction of the two lines. So next, the wave propagation velocities can be computed based on the line parameters. So we can use this formula to find the velocity. So the result show that the traveling wave propagate faster in line 1. This is faster than this one. So which directly affects the timing of reflections and transmissions. Using these velocities and the physical lengths of the lines, The travel times can be calculated, so we can find easily travel lines time. Uh, so uh, uh, this is travel lines for in bus bar 1 for line 1 is equal to 200 microsecond, for bus 2 is equal to 100 microsecond. So a base time step theta is then selected equal to the travel time of line 2, enabling normalizing of this analysis. So this leads to expressing the travel times as multiple of theta. So this one is base time. So line 1 is 2 theta. So because this is 2 times of this one. And finally, the total observation time of 650 microsecond can be converted into 6.5 times of interval. So which provides a convenient framework for tracking successive wave reflection and determining the cumulative overvoltage at different bus bars. So let me add a new student, I think. All right. This slide presents the calculation of reflection and transmission coefficient at different points along a transmission line when a traveling wave encountered impedance discontinuities. So the reflection coefficient is determined using the standard formula Z2 minus Z1 over Z2 plus Z1, which compares the impedance before and after the junction. So in the first case, the reflection coefficient is equal to -1, indicating total reflection with polarity reversal, which typically occurs when a wave meets a short circuit or zero impedance termination. So in the second case, a positive uh, reflection coefficient is equal to 0.333. So shows that part of the wave is reflected while the rest is transmitted. So due to moderate impedance mismatch between the 450 ohm and 225 ohm. So the third calculation results in a negative reflection coefficient, this value, meaning that the reflected wave undergoes a phase inversion. So finally, the transmission coefficient KT is computed as either this one or this equation, giving value of equal 0.545, which represent the portion of the incident wave that continues forward. So this slide continues the analysis of traveling waves at impedance discontinuities by calculating the reflection and transmission coefficients for another junction. So here the reflection coefficient KR323 is obtained using this standard impedance relation, resulting in a value of 0.455. This positive value indicates that a portion of the incident wave is reflected back without polarity reversal due to the impedance increases from 225 ohm to the 600 ohm. The transmission coefficient, this factor is then calculated using the expression of this expression. So we can we can find this value 1.455. Alternatively, also we can use this equation. So a transmission coefficient greater than 1 um, does not violate physical laws. So instead, it reflects the fact that voltage can increase when a wave moves into a higher impedance medium, while current correspondingly decreases to conserve power. So this slide reinforces the importance of impedance matching and highlights how wave amplitudes change as they propagate through different sections of the power system. Okay, this slide illustrates a lattice uh, or Bewley diagram. So I put the other name of this diagram, lattice or Bewley diagram. So which graphically tracks the propagation, reflection, and transmission of traveling waves along a multi-section transmission line with different characteristic impedances. So the horizontal axis represents the physical section of the line from bus 1 to bus 3, while the vertical axis, this is the horizontal axis, vertical axis represent time in multiples of travel time theta. So the initial surge of magnitude 1 per unit originates at bus 1 and travels toward the right when it reached the first discontinuity, bus 2. Part of the wave is reflected with a coefficient of minus 0.455, indicating polarity reversal. So it's come back to the bus of 1, and the remaining portion is transmitted forward with a coefficient of 0.545. As the wave continues forward uh, forward bus 3, further reflection and transmission occur due to the impedance mismatch, so producing coefficients uh, such as 0.333 and 0.455. So you can see here. Okay, each reflected and transmitted wave is then tracked as it travels back and forth between the junctions with its magnitude progressively reduced according to the corresponding coefficients. So the diagram clearly shows how multiple reflections interact over time, creating a complex pattern of wave superposition. So by summing all incident wave components arriving at each bus, the final voltages are obtained. V1 is equal to 1 per unit, 400 kilovolt. V2 is equal to 1.095 per unit or 443 kilovolt, and V3 is equal to 0.835 per unit. So this demonstrates how transient overvoltages can develop at intermediate points in the system due to constructive interference of traveling waves, even when the sending end voltage remains unchanged. So this slide highlights the importance of lattice diagrams as a powerful tool for analyzing transient behavior and insulation coordination in power networks. So this slide explains how the voltages at different buses can be determined by summing all incident traveling wave components obtained from the lattice diagram. So at bus 1, the voltage is calculated by adding the incoming and reflected wave components, giving 1 V bus. We can just replace the values. At the end, we can find 1 per unit or 400 kilovolt, which so for bus 2, the voltage can be calculated in two equivalent waves. First, by summing all wave components traveling to the right of bus 2, we obtain V bus is equal to this value. Alternatively, by summing the wave components approaching from the left, so we can make the same result. And for bus 3 also, we can um, use a similar method. So overall, this slide emphasizes that the voltage at any bus is the algebraic sum of all incident waves at that location, regardless of their direction, and consistent results can be obtained from different summation approaches. So this is a references. Most of this information is coming from this one, Meta book. Let me just stop recording.